Almost every creature that ever lived is extinct, but not all of them were true evolutionary dead ends. Some lineages survived by changing form. Take the archosaurs. They were a group of ruling reptiles that once dominated the land. From them came two branches that are still alive today, crocodiles on one side and birds on the other. Their designs lasted, even if most of the original animals did not. But others were different. They were so bizarre, so unique, that when they vanished, their entire blueprint vanished with them. Imagine a predator with a jaw shaped like a buzzsaw, an elephant with a shovel for a mouth, or a tiny worm covered in spikes and legs sticking the wrong way. These weren't just animals. They were nature's strangest experiments, creatures that completely defied evolution. And speaking of a tiny little worm covered in spikes, this creature is actually the perfect example of an evolutionary dead end. We are talking about Hallucigenia, one of the strangest, if not the strangest animal the Cambrian oceans ever produced. This marine worm looked exactly like what you'd expect from a fever dream. A tube-shaped body bristling with defensive spines on top and 7 pairs of spindly walking legs underneath. But here's where Hallucigenia becomes truly bizarre. For decades, scientists literally had this creature upside down and backwards. The original reconstruction showed it walking on its spines with tentacles waving from its back, an image so alien that it seemed to defy biological logic entirely. But why was this such an evolutionary dead end? Even when reconstructed correctly, Hallucigenia represents an extreme approach to body design that proved completely impractical. Its defensive strategy of being a walking pincushion required enormous energy investment for relatively little protection. No other animal lineage ever adopted this spines everywhere approach because it was simply too costly and inefficient. While other Cambrian creatures developed streamlined bodies, efficient locomotion, and practical defensive strategies, Hallucigenia was stuck being a slow-moving, energy-draining nightmare of spikes. Its closest relatives in the velvet worm family evolved into simple, efficient predators, nothing like this spiky aberration. Today, velvet worms still exist, but they're sleek, practical hunters. The Hallucigenia body plan died with its species, and for good reason. When this creature vanished from the fossil record, evolution breathed a collective sigh of relief and moved on to designs that actually worked. Hallucigenia perfectly embodies the dead-end concept. It looked alien, functioned poorly, and when it disappeared, no animal ever evolved that way again. Jumping from one Cambrian oddity to another, even stranger one, we have Opabinia, a creature so weird that when it was first reconstructed, scientists wondered if they were looking at parts from multiple different animals accidentally fused together. Living in the same ancient seas as Hallucigenia, Opabinia sported 5 mushroom-shaped eyes on stalks protruding from its head, and a bizarre proboscis ending in a grasping claw, like a vacuum cleaner hose with a lobster claw attached. Its segmented body was completely unlike anything alive today. This represents perhaps the ultimate evolutionary dead end, because Opabinia's body plan was so fundamentally different from successful designs that it's almost impossible to classify. The 5-eye arrangement provided no advantage over the 2-eye system that virtually every other complex animal adopted. The proboscis claw combination was an incredibly inefficient feeding mechanism compared to the mouths, teeth, and jaws that other predators were developing. While its contemporaries were evolving toward bilateral symmetry and efficient sensory systems, Opabinia was stuck with an energy-expensive array of eyes and a clumsy feeding appendage that made hunting more difficult, not easier. Opabinia has no clear modern relatives and no evolutionary descendants. Its lineage represents a completely abandoned branch of the tree of life. Every major group of animals today traces back to creatures with much more practical body plans, 2 eyes, centralized nervous systems, and efficient feeding mechanisms. Opabinia stands as proof that being different isn't always better. Sometimes it's just a one-way ticket to evolutionary oblivion. But the Cambrian seas held an even more terrifying dead end. Anomalocaris, the abnormal shrimp, was the ocean's first superpredator, reaching lengths of up to 6 feet, massive for its time. With its pair of flexible front appendages and circular mouth lined with plates, it dominated the seas like nothing before it. Yet this apex predator represents one of evolution's most spectacular dead ends because its design was fundamentally flawed from the start. Those impressive front appendages, initially thought to be separate animals called Anomalocaris, were actually too flexible to effectively capture struggling prey. The circular mouth, while intimidating, couldn't generate enough force to crack through the shells of many contemporary animals. Anomalocaris was an evolutionary experiment in gigantism that came too early. While smaller predators were developing efficient jaws, sharp teeth, and powerful muscles, Anomalocaris relied on size and intimidation, a strategy that proved unsustainable when more efficient predators evolved. Its closest relatives were much smaller, simpler arthropods that eventually gave rise to insects, spiders, and crustaceans. These creatures succeeded by developing jointed legs, compound eyes, and efficient mandibles, everything Anomalocaris lacked. Today's largest marine predators, sharks, whales, and giant squids, all use completely different hunting strategies than Anomalocaris. When nature tried again hundreds of millions of years later, it used completely different blueprints, ones that actually worked. Moving forward in time to the Devonian period, around 380 million years ago, we encounter our first venture onto land, or rather, into freshwater systems with Bothriolepis. This armored fish looked like a living medieval helmet with fins, encased in thick bony plates and sporting jointed arm-like appendages instead of normal fins. Bothriolepis represents a dead-end invertebrate armor design. While protection is usually advantageous, this creature took defensive plating to such an extreme that it became a liability. The heavy armor made it incredibly slow and energy expensive to move, while the jointed arms were too weak to be effective for either locomotion or feeding. But why did this armored approach fail so spectacularly? Because Bothriolepis was solving the wrong problem. Instead of developing better escape mechanisms, more efficient feeding strategies, or improved sensory systems like its relatives, it invested everything in becoming a slow-moving tank. This worked briefly in an ecosystem with limited predators, but as soon as faster, smarter predators evolved, heavily armored fish became easy targets. Other early fish were developing streamlined bodies, better fins, and eventually the backbone structure that would lead to all modern vertebrates. Meanwhile, Bothriolepis was trapped in its evolutionary dead end of overarmor. Today's armored fish, like catfish and sturgeon, use minimal, flexible armor that doesn't impede movement. No modern fish species has adopted Bothriolepis's approach of maximum armor at the cost of mobility and efficiency. While Bothriolepis was solving its survival problems with over-the-top armor, marine predators were experimenting with equally bizarre solutions. The seas of the Carboniferous period, 340 million years ago, witnessed another bizarre evolutionary dead end, Stethacanthus, a shark that seemed to be wearing a medieval helmet made of teeth on its back fin. This ancient shark sported a dorsal fin shaped like an ironing board, covered in tooth-like scales, creating one of the most impractical fin designs in evolutionary history. The ironing board fin of Stethacanthus represents a dead end because it served no practical purpose while creating significant disadvantages. The flat, tooth-covered surface created drag, made the shark less maneuverable, and provided no apparent benefit for hunting, defense, or mating that couldn't be achieved more efficiently through other means. This fin design was so impractical that it defied basic hydrodynamics. While other sharks were evolving streamlined profiles and efficient fin shapes that are still used today, Stethacanthus was stuck with what amounted to a biological speed brake on its back. Compare this to contemporary sharks that were developing the sleek, efficient body plans we recognize today. These successful lineages focused on practical improvements, better teeth, more efficient swimming, and enhanced sensory systems. They understood that in the ocean, efficiency equals survival. Modern sharks are marvels of hydrodynamic efficiency, with every fin serving a specific, practical purpose. Tiger sharks, great whites, and hammerheads all trace their lineage back to Carboniferous sharks, but none of them inherited Stethacanthus's ridiculous fin design. So, if Stethacanthus proved that weird fins don't work in the ocean, freshwater systems were hosting an even more extreme size experiment. Transitioning from the seas to freshwater systems, we encounter Prionosuchus, a Permian-period amphibian that grew to an astounding 30 feet in length, proving that being the biggest isn't always the smartest evolutionary strategy. This wasn't just big, it was the largest amphibian that ever lived, resembling a crocodile that had been stretched on a medieval rack. But size wasn't Prionosuchus's only problem. It represents a dead end in amphibian evolution because it was fundamentally limited by its amphibian physiology. Despite its impressive length, it was still bound to water for reproduction and had the inefficient metabolism and respiratory system of an amphibian scaled up to ridiculous proportions. But why was this approach doomed? Because while Prionosuchus was getting bigger, other lineages were getting better. Reptiles were developing more efficient kidneys, better skin, and improved reproductive strategies that freed them from dependence on water. Being a giant amphibian was like being the biggest, most impressive steam engine at the dawn of the electric age. Its relatives were much smaller, practical amphibians that developed efficient lifestyles in specific ecological niches. Modern amphibians succeeded by staying small and specialized, not by becoming gigantic generalists. No amphibian has ever again attempted the giant apex predator strategy because the fundamental limitations of amphibian physiology make it impossible to sustain. After Prionosuchus demonstrated that giant amphibians were unsustainable, marine reptiles tried a completely different approach to ocean domination: specialized feeding equipment. Moving into the Triassic period brings us to Atopodentatus, a marine reptile that looked like someone had attached a vacuum cleaner to a dolphin's body, complete with a downward curving snout that ended in what can only be described as a biological dustpan, lined with tiny teeth designed for filter feeding. Atopodentatus represents a dead end in marine reptile feeding strategies. While its contemporaries were developing efficient ways to hunt fish, squid, and other marine prey, this creature committed entirely to filter feeding, a strategy that worked for small organisms but proved completely impractical for a large marine reptile. The fundamental problem with Atopodentatus was energy economics. Filter feeding works for creatures like baleen whales because they're massive enough to process enormous volumes of water efficiently. But Atopodentatus was too small to make filter feeding energy positive, while being too specialized to switch to more efficient feeding strategies when food became scarce. Other marine reptiles of the time, ichthyosaurs, plesiosaurs, and early marine crocodiles, were developing streamlined bodies and efficient predatory behaviors that would dominate marine ecosystems for millions of years. Modern marine ecosystems have filter feeders, but they're either enormous, like whales, or tiny, like krill. No medium-sized marine reptile has ever again attempted the Atopodentatus approach because it simply doesn't work from an energy perspective. So, while Atopodentatus was failing at filter feeding in the oceans, the land was witnessing an even more spectacular failure in evolutionary engineering. The late Triassic period witnessed one of evolution's strangest experiments in flight: Sharovipteryx, a small reptile that looked at every other flying animal and decided they were all doing it wrong by attaching wings to their arms instead of their legs. This bizarre glider looked like someone had built an airplane backwards, with massive wing membranes stretching between its hind limbs and tail. This represents perhaps the most spectacular dead end in flight evolution, because Sharovipteryx chose literally the worst possible attachment points for wings. While its contemporaries were developing the arm-based flight systems that would lead to bats, birds, and pterosaurs, this creature was experimenting with leg-based flight, an approach so impractical it defies engineering logic. But why was this doomed from the start? Because legs are for landing, not launching, Sharovipteryx couldn't generate the powerful upward thrust needed for takeoff, couldn't control its flight effectively with wings attached to its landing gear, and couldn't fold its wings efficiently for ground movement. It was simultaneously terrible at flying and walking. Every other flying vertebrate, from pterosaurs to birds to bats, independently evolved arm-based flight systems. Even flying squirrels, which glide rather than fly, use arm-based wing membranes because it's the only configuration that actually works. Modern gliding animals like flying squirrels, sugar gliders, and flying lizards all use variations of the arm-based design. Not one has ever attempted the Sharovipteryx approach because it's fundamentally flawed from a biomechanical perspective. If Sharovipteryx taught us that you can't just put wings anywhere and expect to fly, the Cretaceous period would prove that you can't just change your diet and expect your body to adapt immediately. Fast-forwarding to the Cretaceous period, we encounter one of the most paradoxical dinosaurs ever discovered: Therizinosaurus, a massive predator-shaped dinosaur that decided to become vegetarian but forgot to tell its body plan. Standing 16 feet tall with claws longer than baseball bats, this gentle giant looked like a monster, but spent its days delicately plucking leaves. Therizinosaurus represents a dead end in dinosaur design because it maintained the massive, energy-expensive body plan of a large predator while adopting the low-energy diet of a herbivore. Those famous giant claws, which could have been devastating weapons, were instead used for the mundane task of pulling down tree branches, like using a Ferrari to deliver newspapers. But this approach was evolutionary suicide, because it combined the worst aspects of both predatory and herbivorous lifestyles. Therizinosaurus needed massive amounts of vegetation to fuel its huge body, but its predator-inherited digestive system was poorly adapted for processing plant matter. It was like trying to run a gas-guzzling truck on vegetable oil. No modern herbivorous animals like elephants or rhinos have ever attempted the Therizinosaurus approach of adapting predatory anatomy for herbivorous lifestyle. Much later, evolution, however, would demonstrate how not to over-specialize your feeding equipment. The Miocene epoch, around 15 million years ago, gave us one of evolution's most peculiar experiments in elephant design. Platybelodon, the shovel-tusked elephant that traded elegant curved tusks for what looked like a perpetual dustpan attached to its face. Instead of the elegant curved tusks we associate with elephants, this creature sported a bizarre, flat, spoon-like extension of its lower jaw that made it look like it was perpetually holding a dustpan in its mouth. This shovel-tusk design represents a dead end in elephant evolution because it was a highly specialized solution to a temporary problem. Platybelodon's flat shovel was adapted for stripping aquatic vegetation from shallow waterways, a feeding strategy so specific that when climate change altered these environments, the entire lineage became obsolete overnight. The fatal flaw was over-specialization. While Platybelodon was perfecting its aquatic plant harvesting technique, other elephant relatives were developing versatile trunks and adaptable tusks that could handle multiple feeding strategies. When the shallow wetlands dried up, these adaptable relatives survived while the specialized shovel-tuskers went extinct. Modern elephants represent the triumph of evolutionary flexibility over specialization. Their curved tusks can dig, strip bark, move obstacles, and serve as weapons, a Swiss Army knife approach that served them for millions of years. Today's elephant family shows no trace of the shovel-tusk experiment. Asian elephants, African elephants, and even extinct mammoths all used conventional tusk designs because they simply work better in diverse environments. But not only does over-specialization lead to extinction, the earlier Eocene epoch had already demonstrated that oversizing also leads to the same fate. The Eocene epoch witnessed the rise of Andrewsarchus, potentially the largest land-dwelling carnivorous mammal that ever lived, a creature that took the bigger is better philosophy to its absolute and ultimately fatal extreme. This massive predator, possibly reaching 12 feet in length, looked like someone had scaled up a wolf to the size of a small car and given it the skull of a crocodile. But Andrewsarchus represents a dead end in mammalian predator evolution because it exemplifies the fundamental problem with terrestrial gigantism in carnivores. The energy budget doesn't work. A predator this large needed enormous amounts of meat daily, but its massive size made it too slow and energy expensive to hunt the smaller, more agile prey that was becoming dominant. But why did this approach ultimately fail? Because while Andrewsarchus was getting bigger, its prey was getting faster, smarter, and more diverse. The age of slow, giant prey animals was ending, replaced by the rapid, intelligent mammals we recognize today. Being a giant predator in a world of quick prey is like being a battleship in an age of jet fighters. Other carnivorous mammals were evolving in the opposite direction, becoming more specialized, more efficient, and more adaptable. The lineages that survived developed pack hunting, improved senses and body plans optimized for specific prey types. Modern large carnivores like lions and tigers represent the upper limit of what's sustainable for land-based mammalian predators. No mammal has ever again attempted the Andrewsarchus approach of maximum size because the physics of predation make it impossible. We already know that over-specialization and oversizing are both no good. But that wasn't it. What also leads to the same fate is the wrong lifestyle. And the best example for this is Megatherium, the giant ground sloth from the Pleistocene epoch that combined the worst of both worlds, massive size with minimal energy output. This massive herbivore stood 12 feet tall on its hind legs and looked like a bear-sized sloth that had been hitting the gym for centuries, combining incredible size with the laid-back lifestyle that sloths are famous for. Megatherium represents the ultimate dead end in sloth evolution because it took the already questionable strategy of extreme energy conservation and scaled it up to an unsustainable size. The fundamental problem was that Megatherium needed enormous amounts of food to fuel its massive body, but maintained the extremely slow metabolism and movement patterns of its smaller relatives. This worked in stable, food-rich environments, but made the species incredibly vulnerable to any ecological change. When climate change and human hunting pressure arrived, Megatherium had no evolutionary answers. It couldn't outrun predators like fast herbivores and couldn't defend itself effectively like armored species. Megatherium's extinction marked the end of evolution's experiment in giant ground sloth design. The lesson was clear: don't try to be what you are not. All these evolutionary dead ends didn't just disappear. They were replaced by better designs, more efficient strategies, and more adaptable body plans. Their failure paved the way for the successful creatures we know today, serving as evolutionary stepping stones toward more practical solutions. In the end, these bizarre creatures teach us that being different isn't always an advantage. Sometimes being weird is just being weird, and evolution has a way of correcting its mistakes, even if it takes millions of years to do so.